And we're actually going to divide 11.3 into two parts. Part that you don't need a calculator and part that you do. So this is called areas of regular polygons, and there's two general different types. One in which what happens is you're going to create sort of a triangle that is a special right triangle, which reviews the 30, 60, 90, 45, 45, 90 stuff. And that's the stuff that you wouldn't have a calculator on. And then things that are not special right triangles, in which you have to use trig, which will review SOHCAHTOA. Both of those things are good to review. In which you would have a calculator on. So kind of like we talked about when we were in the other sections, that there would be part of your test that you would have it, part of it that you wouldn't. That's kind of where it comes into play. So it will be broken into two parts. I mean, as of yet, that's the plan. So I'm pretty sure that's how it will stay. We haven't finalized anything, but that's the plan. All right, so the parts of a regular polygon. This is just some vocab. The center of a regular polygon is just like the center of a circle, okay? It's the point at the middle if I had taken this polygon and surrounded it by a circle. So in this diagram, this is a 1, 2, 3, 4, 5, a hexagon inscribed in a circle. The center of that circle doubles as the center of the hexagon. The radius would be from that center to a vertex. Okay, which would also be the radius of a circle. You just won't always see the actual polygon inside the circle. So sometimes you got to envision it. So again, radius would go distance from the center to a vertex. The center, sorry? Has to go to a vertex, yep. The central angle is the angle formed by two radii drawn to consecutive vertices. So if I were to look here, these little red lines here, 1, 2, God bless you. Those are radii, so that this angle here would be the central angle. You could also draw here and here. This would be a central angle here. All of these would be central angles, okay? And then the new word is an apothem. And an apothem is the perpendicular distance from the center of the polygon to the side. So in the diagram that's here, this would be an apothem, okay? But you can draw it to any side as long as it's a segment that goes from the center to the side and has a right angle.
So let me ask you a question about the center.
Mm-hmm.
It's always
the dead center. Yeah, it's like if you won't always see the circle around it, but if you could envision a circle around your polygon, the dead center of that circle is also the center of your polygon. Yep. All right, so again, some vocab because you're going to see that stuff used a lot. Okay, center's obviously at the middle. The radius goes, because now there's two segments that are coming out of that center, right? So you got to be careful. The radius goes center to vertex. The apothem goes center to the side with a right angle. And then two radii form a central angle. With me so far? Okay, the central angles, just like the central angles of an arc, okay, of a circle, are equal to that measure of that 360, the chunk of the 360. If it's a polygon with n number of sides, then you find the central angle by doing 360 divided by the number of sides. So if it has 4 sides, 360 divided by 4. If it has 5 sides, 360 divided by 5. If it has 6 sides, 360 divided by 6, and so on and so forth. Okay, so in this example it says, in the diagram, WXYZ is a square inscribed in circle P. Number 1, identify the center, a radius, an apothem, and a central angle of the polygon. So go ahead and write that out. So give me the center, the radius, the apothem, and the central, and a central angle. All right, so how would I name the center?
point P.
Just point P. How about a radius? PY or PX or XP. Both of those are good. And apothem? PQ. And the central angle? XPY or YPX. Good. I could draw in other central angles, but the only one that was already there is that. Okay? And it could be named either way. Good so far? All right, number 2 says find the measure of XPY. So if I want to find the measure of this central angle, what did we say we're going to do? 360 divided by the number of sides. How many sides are in this?
4.
4. What's 360 divided by 4? 90. Okay, then it wants the measure of XPQ. XPQ is that. How do I know it? Why is it half? Because how do I know it's the angle bisector?
Because the right angle.
Only because of the right angle, and this is isosceles, yes?
Yeah.
With that right angle, isosceles, shared side, I have two congruent right triangles, yes? That's hypotenuse leg. Does that make sense?
Yeah.
Okay. So because that's happening, this angle is to cut into two congruent parts. So if it was 90 before, these are both 45. So angle XPQ is 45 degrees. And then the other one says angle PXQ, which is this angle. How do I know that? It's also 45 because that has to be a 45, 45, 90 triangle. Yep.
So you would know that that cuts it in half because of the base angles.
Because of the...
Basically.
You could get there, but really it's because these are congruent, right? And you have a right angle here. That's hypotenuse leg for two congruent triangles. So every single central angle is divided into two congruent angles as soon as you draw the apothem. So as soon as I draw, like if I had this here and I draw the apothem, these are two congruent triangles every single time, not just with four sides. The angle measurements will change, right? It won't always be 45 and 45. But every single time I draw an apothem, and I have my little right angle there, I've now divided this into two congruent triangles, which will always happen, okay? So that's one of the key components with moving into area, is that we know that as soon as I draw that apothem, those are congruent triangles, which makes this angle divided into two parts, so I can take that central angle and cut it in half. Does that make sense? Yeah? Okay. All right, the area of a regular polygon with n number of sides, side length S, so n is my number of sides, S is my side length, and 1/2 the product of the apothem and the perimeter. A is apothem, P is perimeter. So you can use either of these equations because they are interchangeable. One is 1/2 A, which is little a meaning apothem, times B, big P, which is perimeter, or 1/2 A and S. So if I already have the perimeter, I just multiply it times the apothem and then divide by 2 or multiply by half. If I don't have the perimeter, then I can just do 1/2 A and S. Because N times S is the perimeter. Now notice this is regular polygons. This only works for regular polygons because it divides them into all those different congruent parts. Good so far. That's a formula you got to memorize. Yep. Okay. If you haven't written it down, make sure you write it down. 1/2 AP or 1/2 ANS.
And
That's to find the area of the entire polygon. But again, a regular polygon. All right. So this just says find the perimeter and the area. So we're going to do both parts. A says a regular hexagon with apothem 6. So perimeter is N times S. Area is either 1/2 A times P or 1/2 ANS. But if we've already found the perimeter, if we already find NS, then it's probably easier to do this one. Okay? If I go straight to area, then it's easier to use the bottom. But if I'm already going to find perimeter, then I can use that top one. Okay, so regular hexagon, first of all. 6 sides. N6. I already know that as soon as it gives me its name. What other piece of information am I given? The apothem A is 6. So what don't I know? I don't know the length of the sides. Okay, so here we go. You ready?
Yeah.
Okay. I'm going to draw one triangle in here. And it doesn't matter where you draw it. I usually draw it at the bottom. But I'm going to go from the center down with my central angle. You with me so far? Now, the piece of information I know about this is that these would be, oh sorry, I don't know the radius yet, okay? I only know the number of sides is 6. I don't know the length of sides. I do know apothem is 6. So with a hexagon, what's going to happen is if I were to find the measure of the angle at the top, right, the central angle, so the big one formed by the radii, we said that would be 360 divided by 6, which is 60 degrees, right?
Yeah.
So that whole angle is 60 degrees. What happens when I then draw the apothem through it?
Breaks it up in half.
Now it's 30 and 30 at the top. You with me so far? What does that leave for the bottom right and bottom left? 60.
So 36.
So I just created two 30, 60, 90 triangles. Does that make sense? Yeah? So I'm going to take out just 1/2 of this so that I have one 30, 60, 90 triangle. And I'm going to label the information I already know, which is only at this time 6. Now I can solve for the radius, but I actually don't need it. What I do need is this whole side would be S. So this little segment here is going to be half of S. So I'm just going to put an X there so that I solve for it. And then at the end, I'm going to double it to get the whole side length. So what's the relationship of my 30, 60, 90 angles? The opposite of the 30 is A. Opposite of the 60? A root 3. Opposite of the 90? 2A. The side I'm given this time? A root 3. So I have to solve for A by dividing by root 3. Can't leave that, good. So I rationalize it and simplify it. So A is 2 root 3. That is only this part, which means S is what? 2 times 2 root 3 or 4 root 3. So it is a little complicated, especially at the beginning, but after this point, it is the same pattern every time I get a hexagon. I'm going to get a hexagon, I'm going to draw my central angle, which the top one's going to be 60 degrees. I'm going to draw the apothem, now cutting it into two 30, 60, 90 triangles. They will give you one of those pieces of information because sometimes you can also get the radius, and then you've got to work your way to get the other ones, okay? But it's the same for every single hexagon. We're going to work through the different kinds, but it's the same for every single hexagon. So now I want perimeter, which is N times S. And in this case, that's 6 times 4 root 3, which is 24 root 3. And then I want area, which is 1/2 A times P. Or A and S, but I already have P. 1/2 A, which is 6. P, which is 24 root 3. So I can take half of 6, make that 3, or I could have done half of 24, it doesn't matter. 72 root 3. This is just units because it's perimeter. This would be units squared. Questions so far? All right, look at B. A regular octagon with side 5 and apothem 3. So again, perimeter is N times S, area 1/2 A and, or A times P, or A and S. How many sides? What's N in an octagon? 8. This time they give me S. So all I have to do is 8 times 5, which is 40. they also give me A. 3 times 40. So I can do a half of 40. And this would be units squared. And this would be units. If they didn't give me that information, an octagon is not one that I can split into two special right triangles. So you would do this using SOHCAHTOA, which we'll get to tomorrow, okay?
So on the test, we would have a hexagon if we're going to do this?
If you're going to do the part without a calculator, there's 3 kinds you're going to see. A hexagon's the first. It's a hexagon, a square, or an equilateral triangle, which we'll work through all of them. Yep. Say that again. It's the same thing. Yeah, for hexagon. Yeah, but just what would happen if this one, let's say I gave you the apothem here, I'd have to do 360 divided by 8, and take that, cut it in half. When you cut that in half, it's not a special right triangle, so you have to use SOHCAHTOA, which again we'll get to tomorrow. So today we're going to go through the ones that you could do without a calculator, and then we'll switch gears and do the ones that you have to use a calculator tomorrow. All right, so let's look at C, an equilateral triangle with apothem 8. So equilateral triangle, how many sides? Number of sides? 3. Length of each side, don't know. Apothem, do know it's 8. So we're back to drawing out our triangle because we don't have enough information to just go off of. So this is super fun because we get to do a triangle within a triangle. So I'm going to draw my center. I'm going to draw my 2 radii. This time, to find that central angle, I would do 360 divided by 3. What's that top angle? 120. But I want to draw the apothem in, which just did what to that 120? 60 and 60. And again, I've got a 30, 60, 90 triangle, but this time the 60's at the top, right? And the apothem is 8. So now I can focus in on just that small triangle on the right. Opposite the 30 is A, yay. Opposite the 60 is A root 3. So this is 8 root 3. That's from here to here, which means my whole thing is 16 root 3. Again, like I mentioned with the hexagon, they could give you the radius instead of the apothem on these. You would just have to divide by 2 to get the A and then work your way back, okay? But it is possible to see that. Okay, so now I've got perimeter, number of sides, length of each side. Good. 48 square root 3, and then area 1/2 A times P 1/2 8 times 48 root 3. I can do 1/2 and 8 or 1/2 and 48, doesn't matter which one. 192 root 3. Units and units squared. Okay, so we did a hexagon with the special right triangles. We did an equilateral with the special right triangles. Still good? Okay, next one's back to a hexagon, right? Anybody still comment down? Do you want me to wait? All right, hexagons back to 6 sides. 1, 2, 3, 4, 5, 6. This time they're giving me the side length. So number of sides is 6. Length of each side is 12. I don't know the apothem this time. I'm going to do the same thing I did before. Draw my central angle. We already know the angle at the top would be 360 divided by 6. 60. Then we cut it in half with the apothem. 30, 60, 90. This time the side length is 12. How does that impact that small triangle? Good. I got to cut it into half so that this would be 6. So in my special right triangle where it's 30, 60, 90, this is 6, which means that's the A. I don't need the radius, but I need the apothem, which would be A root 3 or 6 root 3. So then perimeter is number of sides times the length of each side. And the area is 1/2 apothem times perimeter. 1/2 of 6 would be 3. And 3 times 72 is 216. And the root 3. Okay, this is the other special polygon that you can use, which is a square. So without a calculator, I either have to give you the side length and the apothem, or I have to give you an equilateral triangle, a hexagon, or a square, okay? This time it says the square with a diagonal of 10. So we're actually going to talk about a couple scenarios that you could do here because there's more than one way to do this. But let's just say we're going to go with the pattern in which we've been doing. I would have a square. I should have made that filled in. Hang on. Hey. What is happening? Just does not like me today. Okay, square with diagonal 10. So what does that do right now? I've got 2 45, 45, 90 triangles. You with me so far? Yeah. So if that's opposite the right angle, this is my A, this is my A, this would be my A root 2. 10 would equal A root 2. A would be 10 over root 2. Multiply by root 2's, 10 root 2 over 2. Just don't confuse this A with your apothem because this is really the side length, right? Obviously, I know the number of sides, 4. Can you find the area of a square other than using the area of the polygon? Yeah, what's the area of a square?
Times the side.
Just length times width, or side squared, right? So as soon as I get that side, I could do 5 root 2 squared, which is 25 times 2, which is 50. That is one way, probably the fastest way, but that is one way to do it, units squared. The other way is area 1/2 A and S. Right? Oh, did this still have... We also have to do the perimeter, which would be 4 times 5 root 2, or 20 root 2 units.
So we don't even have to find the block.
So you don't have to. No. Not with, only with a square. So now, but if I had this square, let's say, and I wanted to practice the other method, then I can draw my central angle. 360 divided by 4 is 90. Cut it in half. I have 2 45, 45, 90 triangles in that small area.
You can still do it the same.
Correct. And on that 45, 45, 90 triangle, the first thing I was given was the 10 as my radius. That would make this, as my diameter, sorry, diagonal. That would make that 5. So then I would still have to say 5 equals a root 2. A would equal 5 over root 2. 5 root 2 over 2. That would be this part and this part, which is your apothem. And then the perimeter, if this little part here is 5 root 2 over root 2, then this side length is still 5 root 2. And that times 4 is still 20 root 2.
Isn't that just more work?
Sure is. The only benefit to that is you're practicing the motions of going through it, because we're going to have to do it with different ones. But obviously, if they give you the diagonal, it's much easier to go with the right way. The other thing you could see with a square is a radius. Okay, and so with the radius, like if I gave you a square with a radius, you would have to double it to get the, like, think about all the different, like if that was 5, okay, then I would double it to get this and still do 45, 45, 90 triangles. It could also give you the apothem, but that one's super easy because if I gave you this as 5, all you got to do is double it.
Yeah.
And that's the diameter. I mean, that's the side length. So the squares are probably the easiest, okay? But the other ones, you want to go through those motions. So if it's a hexagon, then we would do 360 divided by 6, which is 60. And then we cut it in half to get the top angle. So we end up making a 30, 60, 90 triangle. If it's an equilateral triangle, equilateral triangle, then I would do 360 divided by 3, that's 120. Cut that in half, and it's 60, and that's what's at the top. So it's also a 30, 60, 90, except the top is 60. So that's the difference on those. And then the square with the diagonal is either two big 45, 45, 90 triangles like that, or you draw the central angle and you find the 45, 45, 90s in here. You can do both, so it's up to you. Obviously, I think the second way is a little bit more tedious, but it's good practice for the A&S when you have to do that. All right, questions so far. So the problems you're going to do tonight do not require the calculator, just like we didn't use it today, and that's how you want to practice it. The stuff that we'll add on tomorrow, we will use SOHCAHTOA, and those you will use a calculator for.
So the part where you do like the regular areas of us, the square, we did 5 root 2 times 5 root 2. Why'd you multiply it by 2 instead of dividing?
This part here, you mean? This part?
Yeah.
So it's side squared, right? So it'd be 5 root 2 times 5 root 2, and then the 5 and the 5 give you 25 root 2 times root 2 is 2.
Oh, okay.
Does that make sense?
Yeah.
Yeah, Camilla.
For the second method you did, when you multiply that out, the area, would you get something different? Like,
No. No, you should get the same thing. To 20 root 2, 1/2 a times p. A was